Yeah, hi. Brief introduction. I am Dan Thornburg. I currently maintain LLVM-MOS. I'm also, in my day job, a professional LLVM gremlin. I do unspeakable, unholy things to LLVM for money. And yeah, I'm here to talk to you about compilers, everyone's favorite topic. So thank you for coming to hear me ramble for like 50 minutes about compilers for the 6502. So brief background. This is the kind of arguably boring background section of the talk, but it's important to do that so everyone's on the same page for the cool stuff. My point of view. LLVM-MOS, what is it? It is a LLVM-based C and C++ toolchain for the 6502 and the things that use the 6502, its platforms. So there's actually a lot in this sentence. I will go bit by bit and break that down and define things. So first, we can start with the 6502. If you're here, I'm wagering that you know what the 6502 is. If not, it's a 1975 CPU, 8 bits. It was used in lots and lots of cool stuff. Among my favorites, the NES, the Ataris, Commodores. Like, it was kind of one of the two big CPUs that defined the 70s and 80s, the other being the Z80. And it's just a fixture of computing history and pop culture. It made it into jokes in Futurama. The Terminator famously was using 6502 assembly, even in the distant future, stuff like that. It's a great chip. A little bit about it. It has a stack that can be used for local variable storage or return addresses, but it's only 256 bytes, which is really scarce compared to what you expect from a modern system. It does 8-bit arithmetic, but it has, say, 16-bit addresses, so you can't, do address arithmetic in a single cycle like you can on pretty much every modern system. Has only 3 registers. Modern systems typically have somewhere between 16 to 64, so that's rough. And its memory is weird. It has something called a 0 page, which means that the first little bit of RAM, the first page, 256 bytes, is very special. There are instructions and addressing modes that use this specifically, and that also is very weird. There aren't systems these days that tend to have dramatically different ways of treating different sections of memory based on their address. So, 6502. What about the systems that used it? Well, here's the ones that we support in LLVM-MOS. This is a pretty big list, and a lot of these are very, very different from each other. Notably, I didn't work on most of these. We've actually had really, really good success in people contributing back-end support to our software development kit. Or SDK. I'm going to say SDK a lot. In your head, mentally replace that with software development kit if you like. Also, this list is a lie because if you take, say, Atari 2600, you can break it up into 2 subtargets. The Atari 8-bit, we have 4 subtargets. The NES is even worse because every single NES cartridge has a different chip in it, and that chip completely controls the memory layout that the processor and graphics chip sees. They have their own registers at different addresses to configure them. The diversity of 6502 systems is tremendous, especially compared to Z80 systems, which were intentionally designed to be far more uniform, except for their disk formats, as I learned today. Notably, also, we have at least one target that uses CDs, so that's a thing. How about what it actually does? Well, it takes C and C++, a human-readable language, and kind of, arguably C++ is human-readable, and converts it to something that can actually run on one of these systems. So if you're not familiar with what a toolchain is, a compiler is actually one small part of that. You go from human-readable code that says do the thing, and then you compile it to kind of an unfinished do the thing in something close to, but not quite like what the machine expects. That's called an object file, and that object file will have holes in it. Holes that are shaped like, say, printf, or functions that do things that the system can do, but your code doesn't actually need to know how you do it. Then you combine that with libraries of already compiled stuff, either from your own project or from a software development kit, and you link them together to produce a final object. The linking is configured by something that's typically called a linker script, which says, okay, I'm going to place all of this stuff, I'm going to resolve these addresses, and here's how I'm going to do it. Here are the constraints on the layout and the regions that are available so that I can actually pack everything into something that will fit on the machine that you're going to be trying to run this on. And then the output is a nice, friendly binary that you can put in an emulator, that you can load onto a disk, and then actually get to run. And so the ideal version of this is that you just clang this, the clang is the name of the C compiler, and then all of this stuff happens kind of as a result of that, and you get an image that you can just immediately run. So in terms of what we actually support for C and C++, we are LLVM, which is one of the main modern compiler things. So we get the new stuff. For C23, we have my personal favorite, number embed. If you want to include a file in a C array, you can just number embed the file in there, and it'll come in as a binary. Very, very slick. All the weird stuff, variable length arrays, inline, we got real bool. We also support C++, like recent C++. So you can do lambdas, you can do const expert, you can do all of the C++ nonsense that your heart desires, except exceptions. No, just no. We're not, no. So that being said, we are pretty serious about standards compliant. What we have there is pretty extensively tested for standards compliant, and we take that seriously. But compilers are big, libraries in particular are big, so there are holes. Typically, if you run into one of those holes, the compiler will crash saying, I don't know what to do with this, I'm sorry. Or you'll try to access some library and it'll be like, I don't know where that is, I'm sorry. And then you file a bug report or add support for it yourself, please. So yeah, I also should talk about LLVM because I've said that word like half a dozen times and only cursorily defined it. So first, LLVM doesn't stand for anything. It used to, now it doesn't. That happens all the time in computing. What it is a compiler infrastructure project. So it's kind of one of the big three compilers that's used in industry. GCC and Visual C++ are kind of the other big two. And it consists of a library of tools that can be put together into a chain of tools, a tool chain. So Clang, C++ compiler, runtime libraries for things like multiplication and division if you can't multiply and divide, C standard library, C++ standard library. Notably, it has some real nice features for people. It has a ClangD server. So if you're used to something like Visual Studio Code that gives you, where is this function defined in my giant project? And you can click on it and go to the definition. You can do that in LLVM-based projects, including LLVM-MOS, using the ClangD language server. So we actually do have like go to definition and IDE support for our SDK, which is cool. You also have automatic code formatting, and you can lint and automatically fix up issues that Clang Tidy finds. So it's a pretty complete LLVM distribution. So that's kind of the background part. That's what our project is. Okay, I can just no. The next obvious question is what could I do with this? I'll kind of go chronologically. This is where I get to show off all of the neat crap that people have made with this that I've scrounged from the internet. So this was actually made for me when I give a talk on this like a while back at Euro LLVM. MRK put together a little demo in Rust for the Atari 800 with the Rust crab moving around, which is fun. But notably, this is doing interrupty stuff, and it's written in 500 lines of pretty high-level Rust. And that's something that we've kind of been interested in enabling for people, is writing kind of high-level-ish code for this processor and having it work okay, which is not something that you can do with CC65 or one of the older generation of compilers. You tend to have to write very stilted C. You're constantly aware of the compiler. With LLVM-MOS, you don't have to be quite so aware. To take that to the other extreme, something much more recent, here is a game made by a trio of people whose names are up here. This won third place in the NES Dev Compo 2023. And this is 6,500 lines of, again, very high-level, very readable C++. I think it's a two-player game where, sorry, I have played this. It's a two-player game where one person plays Tetris, the other person controls like a guy in a maze that, they interact with each other, which is interesting. But it's interactive and fast, and it's written in pure high-level language, which is something that for NES Dev was kind of considered off limits. You tended to have things that were written in C65, but again, you had to be very, very aware of the limitations of this, know when to drop out into assembly, you had to get good at using the tool. Kind of the most extreme thing I've seen someone do with this is they took an off-the-shelf RISC-V emulator, that had just enough stuff in it to run the Linux kernel, and then they ran the Linux kernel on a Commodore 64, a real one. So there's a YouTube video of this. It is a collection of YouTube videos because it's 48 hours long. But they got it to boot, by God. And someone has now run Linux on a Commodore 64, which is the best thing ever. I did not watch the Trit stream, unfortunately. It was like watching paint dry. Like characters would drip out one at a time. It's great. It's a great project. This is my personal favorite. Someone took dev/ubu random, which is a much better version of urandom, the Linux random number generator device file, which instead of producing, normal boring pseudo-random numbers for cryptographic purposes, no, it produces random catgirl noises. So somebody made this, gave it a beautiful NES text box, and ported this again already existing C code that they didn't have to touch at all, the Markov generator, and it works great at a high speed on the NES. And I have it on my NES on an EverDrive, and I show it to people anytime I get the chance. Other random stuff. Somebody ported Zig. That's cool. I spent an entire Christmas watching Juka Jalanki, whose name I inevitably butchered. Write a custom C++ IDE on his Commodore that over a network link sends code out to be compiled by LLVM-MOS on his PC, and then sends it back so that he can have a fast compile run loop, using a web browser that he wrote on the Commodore to access, again through the network, the Advent of Code, and check his answers. Did the entirety of Advent of Code on a Commodore 64 using LLVM-MOS. It's actually one of the most insane projects, and I was just I cannot gush enough about the madness of this. That at this time, our standard input and output library wasn't finished, so he just started writing his own, and didn't submit it upstream, which I'm still a little but mad about. Somebody ported CP/M also, taking advantage of the fact that we have kind of more relocatability due to being a more modern compiler architecture. And David Givens also, same guy, used similar flexibility in our SDK to hack apart and build an assembly-only SDK for these random Tony 1.8-inch Alibaba game consoles that you can buy for $1 that are all apparently 6502 based, but encrypted in a weird way. It's great. There's a good YouTube video on it. I highly recommend. So yeah, this is a lot of cool stuff that people have made with this C compiler. I still hear this constantly. You can't do C on the 6502. Stop trying. You're crazy. Why are you it's remarkable how often I hear this. Shades of the 6502 is not a good compiler target. I would have believed this if it was just my project. And admittedly, we're not great at it. We don't produce that good a code. I'm still, again, butt mad at how good our code is. And I'll have more stuff on what I'm trying to do to fix that and make it better. But there are also compilers that have currently lapped us. Again, I'm kind of mad about that. So there are a generation of new C compilers that kind of prove this wrong. What I think a truer version of this statement is that it's difficult to compile C to the 6502. And difficult in this term meaning straightforward. It's not straightforward. There's kind of a standard grab bag of compiler techniques that you use for modern systems, and they work really, really well for those systems. In large part because the hardware people responded to the compiler people. The whole thing about RISC, if you've heard of it, is, hey, compilers are only using 10% of our instructions. We should get rid of the rest of them and make those really fast. Hardware people care about what compiler people think, and compiler people care about what hardware people think, and they have trotted off together into the sunset holding hands, and there's rainbows and stuff. But for the 6502, there's not. And that means the compiler people have to do really weird nonsense. But you can, and we did. And we're not the only people that have. So it makes it worse. So what is the worse? This is the fun part of the talk to me. How do you actually do this? I'm going to give you a crash course on how a modern compiler works. Now, I have now something like for 35 minutes in which to do so and get through the rest of the talk. There is no chance you're going to be able to go build a compiler after this. But you might actually be able to orient yourself in LLVM and have a vague sense of how things are actually put together, which would be cool. So I'm going to see if I can get through that. Here is the compiler part. This is the actual compiler. This is Clang compiling. And this is what we would call the front end. So you start with C and C++. The next thing that happens is you parse it. You could think of this as saying, what does it say? We're just interested in syntax at this point. We're not interested in meaning. You could imagine this language being like a human language, and you can separate out the meaning of a sentence from the literal words in the sentence. So at this point, we're dealing with words, and we have a data structure called an abstract syntax tree, or AST, that is kind of a mapping of all of the words and how they relate to each other. This is an adverb. This is a pronoun in English. There's, completely different terminology for C, but it's the same principle. Then you semantically analyze it. You said, I know what this says. What does it mean? And this is where you check for things like semantic errors, like, you have a zero size type, or, just tons and tons of stuff. You size things, you get a sense of the meaning of the C and how it all relates to each other. And then what you do with that meaning is you vomit it forth. And it is amazing how literally Clang does that. So there's an intermediate representation that looks kind of like a high-level assembly, and that's what LLVM is based on. It's called LLVM's IR, intermediate representation. And what Clang does is emit, for each of these bits of meaning, the stupidest possible bit of assembly that could possibly do it. Literally awful and dumb and bad. So for an example, like if you have a local variable, int x, then, that could go on the stack. Like, it'd be terrible if it did. Int x equals 2. It's not even read anywhere. It will say, I'm going to bump the stack pointer. I'm going to store 2 there. I'm going to record that that's where I stored it. And then I'm going to, clean up the stack afterwards. Like, it'll emit all of that, even though it's not read anywhere and it'll all go away. And this is to keep Clang simple, because despite doing the dumbest possible bit of code gen you could imagine, it's still friggin' enormous. Clang is a monster. Like, C++ is so insanely complicated that even just doing the stupidest possible thing takes like hundreds of thousands of lines of code. But it's not acceptable, the stupidity that comes out of this, unless you're compiling at 0 with optimizations off. Don't compile at 0 in Clang with optimizations off. For historical reasons, that's the default. Don't do it. It shouldn't be the default. It really shouldn't. Like, Clang, computers are really fast, okay? I'll give you that. But we've had, say, in LLVM-MOS, people try to compile at 0, and like, I think hello world is something like 50K on the 6502, so it's bad. But we're gonna get it. We're gonna knock it down, and the place that we knock it down is the middle end. And I'm not going to talk about how we knock it down even slightly, because it's really complicated and there's a million pieces to it. But you could think of it like this. We've got this IR that does something stupid. I gave an example. We got a local variable. I'm going to bump the stack. I'm going to do a bunch of manipulation, but it's not even used. So you could have a pass that goes and looks for things that aren't even used, and then deletes things that pertain to them. And then it notices, the stack bump isn't used because we don't use the stack at all, so it deletes that. And you can just recursively get rid of crap that you notice isn't used. That's an example of an optimization. And I put all such optimizations in a circle called opt. So we do that. Now we have nice, sparkly IR, written at an extremely high level that looks absolutely like nothing that you could do on the 6502. So the next thing that we do is translate it to a language that looks absolutely identical to it. We do nothing. The reason that we do this is that LLVM's IR is fixed, but this is the part where we're going to start massaging it and making it look more and more 6502. And that means we need a very flexible representation for the contents of our binary. It's going to start picking up 6502-isms. So we need to be in a position where we know less and less about what it means and start manipulating it again more like what it says. You could think of a compiler as going from something that says something to something that says something. You build up meaning, and then you gradually discharge the meaning as you get closer and closer to the machine code, until you get to the point where you're assembling stuff and the compiler's just like, here's an instruction. I don't know why that instruction is there. I'm just going to put out numbers for it. So you're discharging meaning gradually, one bit at a time. And that's kind of the overall flow. So we'll continue on in that fashion. The very first thing that we do is discharge a little bit of meaning. Right now, this will be in terms of, I want to add, say, these two 16-bit numbers together. And on the 6502, you can't add two 16-bit numbers together. You can only add 8-bit numbers. So that's illegal. So what we do is we legalize it. We split that 16-bit add into two 8-bit adds. And we don't know anything about where they're going to get put. We don't know anything about anything. All we're doing is splitting it into instructions that are more plausibly legal on our target. And now we've lost information. Again, we lost some of the meaning of what you're trying to do. And now we have just a collection of operations that we'd like to do, that we're convinced do the same thing. And then, once we have a set of plausibly legal instructions, we can find 6502 instructions that map well to them. And here we need to insert a lot of fakes and stuff. But for, say, like an 8-bit add, well, that's going to be an add with carry. That's really the only way to add. Unless you're adding by 1, and then it's an increment. But you might be able to do an add with carry with 1, depending on the situation. So we'd say insert a pseudo instruction that allows you to switch out based on whether it ends up in a, in a location in memory or in one of the, you can imagine kind of doing this, just sort of mapping these abstract operations onto kind of virtual or real 6502 instructions, but still leaving it kind of loose where things get put, what the arguments are. That's instruction selection. The next important thing that happens is register allocation. You go through and you actually find globally, where am I going to put everything? And you try to do that while minimizing the amount of work that gets added by copying and moving things around. Notably, this is somewhere for the 6502 where the LLVM's algorithms are really weak. The register allocator in LLVM is kind of designed around the assumption that copies are free or close to free, and they're not on the 6502. They're really, really not. And there's a lot of other assumptions about that really make it not do well. But in any case, it does kind of work. Like, it works okay. It's definitely the weakest part of the compiler, but it produces okay, acceptable sort of results. Then there's just a bunch of other trivia to take care of. Once we've allocated registers, we know what fits in registers and what doesn't. So we can take the values that don't and put them on the stack and lay out stack frames. So we do that. Then once we know the stack frames, we have basically a final set of instructions. And we can start doing things like laying out these blocks of code that jump to each other. Some jumps are nearer and some jumps are further. So this is kind of the first point where we really have the ability to say, oh, this branch is out of range. The 6502 can only branch between, say, 127 bytes backwards and 128 bytes forward. If I'm wrong on that, please don't crucify me. I write compilers. I do this so I don't have to write assembly. I'll look it up if I need it. I guess I'll say that. So yeah, you can solve problems like that until you actually get down to something that is morally equivalent to assembly. Again, discharging one decision at a time. And then you have assembly and you can write it out. And there, of course, is a pass in LLVM that does that. So there you go. That's a compiler. That's how it works. Again, I didn't specify very much about how specifically you do this for the 6502, because I hinted at some of the weird nonsense that we do, but now I will talk about the actual weird nonsense that we do. So first thing I'll talk about is the frame layout process, because this is kind of the thing that people used as, for the longest time, the main reason that you couldn't do good C on a 6502. So in C, you got local variables. You got int x, you got int y, you got arrays. Traditionally, they go on a stack so that you can recurse and do stuff like that. Like C's mental model kind of depends on there being a stack that grows downward or upward or whatever. You can't use the hardware stack on this because people will make arrays that are like a kilobyte and it won't fit in 256 byte. So typically, the simple way to do this, what CC65 does, is you maintain a stack pointer somewhere in memory. 16-bit pointer, you bump it, but you can see on the left how many cycles each of these things takes, and it's pretty rough. To bump the stack pointer takes 10 cycles. To restore it at the end, another 10 cycles. Just reading a variable off of that stack is 8 cycles, and that's bad. That's real bad. Particularly, the costs of statically allocating memory, not using a stack, not using local variables, but having everything be global, is on the right. And it's pretty dire, the difference, especially because, it's not a very fast processor for the most part. Like, every cycle counts. But notably, programmers that write by hand almost never end up using stacks. What is this amazing technique that allows developers to not have to use stacks for their programs? Well, you can kind of just imagine the call graph of your entire program and notice that, oh, most of these functions don't recurse. They call a thing that calls a thing that calls a thing, but those chains are not cyclic. But you might have a little section of your program that you designed to recurse because you're doing quicksort or something, and those sections are cyclic. So what I can do is I can take the cyclic parts and I can make them use a stack, and then the non-cyclic parts I can just go through and churn through and assign all of their addresses statically. So we do that. We do a whole program analysis using LLVM's link time optimizations and just look at your call graph statically and determine which parts can and can't recurse and do that. In fact, we can even let things like C and G here, which because of the nature of the call graph cannot possibly be active at the same time. One can't call the other, and the other can't call the one. So you can have them overlap, which is something that assembly language programmers could do, but tend not to do because it makes the accounting very, very difficult. And one of the great things about compilers is that they're accounting machines. They can take care of all of this stuff for you, which is one of the reasons that you can get slightly better code out of a compiler. Now, I'm not claiming we do beat the human. We absolutely, categorically do not. But this is an aspect where we can beat the human sometimes. Honestly, in our experience, that more or less takes care of the stack pointer problem. Most code that we've seen people write, all of those examples that we had, very few of them actually use stack pointers at all. The compiler does a good enough job of getting rid of that memory is allocated statically, just like assembly programmers tend to. So the next big problem is the register allocator. There's 3 registers. Worse than that, LLVM, one of those constraints is that it assumes you can copy from any register to any other. You can't. You have to go through the I register, except I think on the 65C02, which is nice. We take advantage of that TXY and TYX instructions when we can. But LLVM's register allocator hates this. If you have 3 registers and you can't copy between any of them, it will just bail. It will say, your constraint problem was too hard. I can't solve it. I will now crash. And that's infuriating. That's not something we want the user to have to deal with. But I mean, you imagine how hard of a problem it is. You've got 3 places to put things, but you got a ton of values flowing around in a routine. Like, I wouldn't expect to be able to do that. But assembly language programmers don't do that. They use the 0 page. And that's kind of what the 0 page is for. It's a collection of places to put values that are almost as fast as having them in a register. In fact, for things like pointer accesses, you can only have them in the 0 page. Like, they are kind of like registers. And they have those properties that we're looking for. There's a lot of them. You can copy between them relatively quickly. They're very homogeneous. Like, each 0 page location is just like each other 0 page location. So we, and again, this is a trick that is used in several other, I'm going to call them 2nd gen C compilers for the 6502. We treat them like registers. We actually present them to LLVM as if they were architectural registers. And then really late in that pipeline, right as we're about to spit out assembly, we break the lie and turn those into memory accesses and let the very last stage of the compiler and linker take care of actually resolving those to real memory locations. And this pleases the LLVM register allocator. It is perfectly happy with this setup. The main issue is that they still don't actually have fast copies between them. The register allocator thinks that copies are much cheaper than they actually are. It still will spuriously copy between, imaginaries. In LLVM code, you do tend to see spurious copies between imaginaries being like quite a bit of the cruft that we generate. And that's one of the reasons that I'm very actively working on trying to improve that situation and make it better. So the other big thing that is hard is what to do once you actually have what I'm going to call relocatable code, which is code where you have all of the code, you know what everything points to, but you don't know where you're going to put it yet, what addresses you're going to actually assign to it. The constraints that are given by these platforms to where you can put things are crazy, actually insane. And that's one of the things that has kept people writing assembly, because even if you are using a high-level language, you ended up having to take a lot of that burden on yourself. So there are tons and tons of executable file formats that these systems actually will load in their ROMs and operating systems. If you are putting in a cartridge and it's going to boot off of that, well, there's tons of cartridge formats too, both for emulators and for things that write cartridges and for the actual layouts in memory. We have CD ISOs. Like, how the heck is a compiler going to deal with that? So we needed to pick what exactly it was that we were going to have our compiler output to. It clearly couldn't be any of these executable formats because, our tooling needs to take it. So it's going to be ELF. It's going to be a modern object format that compilers know how to deal with. ELF is not just used by us, but it's also used by embedded developers everywhere when they're going to have something temporarily float around that they're going to convert to their own bespoke nonsense. That's just kind of the going standard of how I've seen people do this. So we'll need a way to make final binaries from ELF. And doing so will also require tons of information from the user's configuration, from the link, where things got put. And I'd also really like you not to have to write custom C++ and LLVM and get it linked into the project to be able to port the compiler to a new platform. To me, that would be something that would have really killed LLVM-MOS, and we would not have had as many targets that people have contributed as we had. So those are constraints. What we came up with for this is in the language where you define where everything gets put, I added a new construct, which is an output file builder. So what you can do is you can say exactly the contents of the file that you want to come out from this. It'll make an ELF file kind of as a side output, but also you can place individual bytes with any expression that the linker can see, the address of anything with any arbitrary math done to it. It has ternaries, so you can switch out values. In addition to this, you can also place any code or data sections that come into the linker in line and alternating with those expressions. So you can kind of build section by section the contents of the output file that you want. You can also trim those and collect only sections of them, and you can also trim them to 0. So you can conditionally include contents based, again, on things known to the linker. So this language we found has been flexible enough to represent every system except for CD ISOs. We weren't able to figure out a way to make Joliet ISO files. That would have been nuts. Maybe it's possible. I don't think it's Turing complete, but we maybe could make it so. But that seems like not a good use of time. But mostly this satisfies. So I'll give a specific worked example because it's beyond horrible. I took this on because I wanted to see if it was possible, as a personal challenge, to see if you could have a configuration for the NES, one of its mappers, where all of the different ways of configuring this thing would be built into the SDK, and you would just configure it. You'd say, I want it to be this big, I want it to have this bank layout, I want it to have this many banks, and then the linker would just take care of it for you. And I was actually able to do that. Now, to understand why that's insanely impressive, and I'm a very cool guy, you need to know how awful the MMC1 is. So this is the cost-reduced chip that Nintendo first introduced. I think it was their first ASIC mapper. A mapper being a chip which allows different banks to be presented to the NES from the cartridge, which had quickly grown beyond what it could actually access. Like the 64K that it had available, only small chunks of it were actually, didn't overlap with I/O hardware in the NES. So, there's constraints on what the CPU can see. So this is a chip, and when you turn it on, its internal state is random. Now think about how bad this is. This is a chip that defines what addresses the NES CPU sees when it comes on, including reset. The first address that the CPU will load is random. Not quite. Not quite. You know that it's always the last 4 bytes of one of the banks. Sorry, the last, wherever the reset vector is. You know that it's going to go to the end of one of the banks. So you need to put reset code in every bank, the same reset code, to set up this chip and get it into a sane, consistent state. And there were kind of a few blessed ways to do this. One of them famously was pulled by NES developers from the Barbie game, and so it was called the Barbie reset. I don't know why specifically that, but yeah. So we needed something like the Barbie reset, but copyrightily distinguished from the Barbie reset, although I think it's 6 lines of code, anyway. So you need reset code in every bank. Worse than that, you don't know how many banks there are. Like if you were trying to just put this out there, you can configure, you should be able to configure how big your image is. So you need to produce the correct number of these at the end of each bank when you don't know how many banks there are, which, it's bad. And we didn't want people to have to write their own complete custom scripts from scratch to, set all of this stuff up, which is the going standard. If you want to make an NES game, usually you just copy paste some giant project from someone that did all this. And I wanted you to be able to say, NES equivalent hello world compile, it comes out and it works on the MMC1. But we were able to get this working. So here's fragments of the linker scripts that allow you to do this. So you don't know how many banks there are, but we have a symbol that you can set in your program anywhere for the PRG ROM size. And then we've got these banks where you can put things in. And you can see the length. This is a ternary expression that switches the length from either the size of a bank or 0. So if you try to put things in a bank that you didn't, set up, then it'll complain saying, I don't have room, this bank is of size 0, which admittedly not the best error message, but it'll fail the link, it won't give you garbage. Notably, also, the length is reduced by 12. That's the length of the reset vector that has to go into every bank. So it'll reserve room for this reset vector automatically, and you don't have to do anything. We'll also make a place for the reset vector. Now, this is going to be a weird piece of code because it's not actually going to know where it's going to run or what bank it's going to be in. So we're going to just arbitrarily throw it in some bank, and we're going to say that it starts at the end of that bank minus 12, and its length is 12. And then we're going to write a NES ROM file. So I can include in here all of the stuff needed to write an iNES image header, which will allow you to run it in an emulator or flash it to a cartridge. And then beyond that, first I'm going to include the full contents of the first ROM. And keep in mind, this is minus 12 bytes. And then I'm going to include the reset. But I'm only going to include it if that bank is actually present. So I'm going to have another little switch. Is the length of the PRG ROM non-zero? If so, we want 12 bytes. Otherwise, we want no bytes. And you just keep going in this fashion. Each of these PRG ROM banks will either have a length that is 0 or non-zero. And then the reset will switch on that and produce either 0 or non-zero bytes. So this one expression will automatically produce all of the reset vectors and all of the nonsense that you need for any size that you configure without you having to do anything. And this is all just checked into our SDK. You actually can just set the size to whatever you want, and there are a dozen other values and variables that you can configure for this thing that have similar logic in the linker scripts to deal with it. You can just put your code in there and it'll work on an MMC1, which is so hostile to users that people had actually been warding people off of using it. There are definitely easier mappers to use. But I took this one on first just to see how hard we could go. And what we found is that this set of techniques allowed us to develop good support for pretty much any other mapper that we cared to, which is why we ended up with such a sophisticated library of them, because people were just able to copy paste this stuff and modify it to get support for all of the other mappers. So there is one other big thing I talk about in our software development kit, which is libraries. It is actually really hard to port a C and C++ compiler. The compiler tends to assume that it has access to a bunch of stuff. If you, in C, copy a struct from one place to another, the compiler is within its rights in the modern day to emit a call to memcopy. And there has to be a memcopy. If there's not a memcopy, then it won't link. So the compiler just assumes that there is stuff that it can do, and you have to make sure that that stuff is doable. So we didn't want people, if they were porting this to a new platform, to have to deal with that. So what we did is we made our SDK hierarchical. So there is a common SDK target that includes the bare minimum parts that are necessary for anything that runs C. And then other targets depend on that, and other targets depend on those. So for instance, we have an NES target that depends on common, and it fills in holes that any NES project are going to configure a certain way, and leaves other holes that would be more specific to specific mappers. And then those mapper targets, like MMC1, depend on that NES target. So with this organization, you never are overriding anything. There's never defaults that you have to figure out are there. You're plugging gaps and filling holes and getting more specific as you go outward. And notably, these are all real targets. If you want to, you can take your project and you can compile it against common. And if you fill in enough holes in your code, it will run. So this typically has been the way that I've bamboozled people into porting our SDK to new platforms. They've wanted to write a project for this thing we don't support yet, and I've taught them how to do it using the common target. And then they accidentally ported the SDK, and I was like, oh, hey, would you mind upstreaming all of this code that you wrote for this platform as a new target, which they could do easily because all of the code necessary to do so was already in their project. So, with a little bit of goading, we've been able to accrue quite a lot of these targets, which this is old news if you've ever maintained an open source project. Like this kind of Structuring things so that it's as easy as possible for people to contribute back is one of the things that tends to make projects more successful rather than less successful. Like, it's the case now that although I am, I guess, BDFL for this, I'm not the majority contributor anymore. Like, most of the commits don't come from me. They come from people working on SDK things, more esoteric things that people know more about than I do. Another interesting thing that we had to deal with, LLVM only supports UTF-8, and that's probably going to stay. All of these things have their own weird character sets, too. But here, we were able to use some C++ magic, and I really like this. So C++ has a wonderful, wonderful feature called user-defined literals, where you can take a string, and you can put something like _u next to it. And _u is a function that you can define that is a const expr. So if you're not familiar with C++, what that means is it is a function that you can get the compiler to run in itself at compile time in your code. And one of the things you can get through horrible C++ nightmare logic, that function to do, is to make a variable that has contents that, again, are also computed at compile time. So the long story short, we were able to convince the compiler to transform UTF-8 strings to various target character sets at compile time. So in particular, what this lets you do is you can say on the Commodore 64, put in like a little smiley face emoji or a little heart, or I don't remember exactly what Petsky has. You can put in a Petsky character directly in your editor and then use this user-defined literal, and the correct value for that Petsky character will come out into your program. And you may be wondering, how can I put a Petsky character into my very modern text editor? Well, the answer for that is that recently Unicode got the symbols for legacy computing added to it. So it actually has a complete character set for almost every 70s and 80s home computer system in it. I don't know if you guys knew this, but you can actually directly today type Petsky characters into your code editor. And have them in your source text. And since it's UTF-8, we can take those Petsky characters as they are and convert them to, so you could do, if you wanted to, Petsky art in strings in a C file and printf it out, and it would work. I consider this very cool. Okay, getting towards the tail end of this, I'll also talk about, since I am actually day job LLVM guy, incidentally, the way I got started at my job was by working on LLVM-MOS and then showing it to the people that did kind of Fuchsia specifically. I work on the Fuchsia toolchain team, and I showed them LLVM-MOS and was like, here, can I do LLVM things with you? And they're like, yes. Cool thing. I think it was a little more elaborate than that. You'd have to ask them. But yeah, because of that, incidentally, we ended up taking on more and more responsibility with embedded teams at Google who work on microcontrollers, and boy, oh boy, do microcontrollers look like the 6502. Not quite, but a lot of the same challenges there. Basically, whenever you don't have a memory mapping unit, things look more 80s than they do not 80s. So there have been some weird crossovers between things that LLVM-MOS wants and things that my job wants, to the point where I don't even know if this is a hobby anymore. I'm just always at work. Anyway, sorry, that was a weirdly personal digression. Okay, here's something that I did in LLD. This is upstream, by the way. This is in real LLVM. And it's something that I was asked for in LLVM-MOS. Now, we can't actually really make use of this yet because we need automated banking support, which I'll get to later. But this is actually a slide from a talk I gave at the LLVM dev meeting, which is hilarious. So this is kind of how you, in a linker script, if you have different RAMs that are placed in different places, you want to take your program and you want to put some things here and some things there, just so it fits, you know? Maybe you don't even care. Maybe you don't, there's no differences between these, but I've got this amount of RAM here, this amount of RAM there. They're separate from each other in memory. LLD and GNU LD expected you to play Tetris with your program. You had to actually go file by file and say, this file goes here, this file goes there, this file goes here, and you had to try to make it fit. And this is bad. Like, this is the kind of toil that computers were designed to free us from. Like, this is, it feels trivially automatable, and it is. In fact, there was a feature in GNU LD that no one had ever heard of. Like, seriously, I did a Google search for this. flag. It's called enable non-contiguous regions, and that doesn't sound like it would do this, kind of. I mean, maybe it sort of does, but no one had ever talked about this. There was like a single Stack Overflow post and the GNU LD manual, and that was it. But we added that feature to LLD, and that actually kind of solves the problem. But we did one better. We made a new syntax for this that doesn't require you to pass a weird flag. So you can just say, oh, I've got this data, and I'm going to put it in a class. And then I'm going to tell you, here's all the places that this class can go. I don't, this data needs to be put here or here. This data needs to be put there, there, or there. And then the linker just figures it out for you. It first tries to put it in the first place until it fills up, and then it tries to put it in the next place. And it keeps, bumping it down the line until you run out of places to put it. And this is how I would have always assumed linkers put things in places. Like, that's the dumbest, most obvious algorithm for this. And they didn't, for various reasons. It actually ended up being very, very complicated to write. But we got it working. It's good. You can use it. It's going to be an LLD forever. So you can use this now. What I'd like to do is have this work with NES banks, but it can't for subtle and complicated reasons. Another thing we added, linkers have garbage collection, so they have the ability to remove code and data that you don't actually reference. The most common reason that people notice this is that they notice that their code is calling something weird that is huge, and they don't know why. Like, they pulled in a thing that pulls in a thing that pulls in a thing, and then suddenly there's like this Bluetooth library that got added to your project. And I'm like, why am I using Bluetooth? Like, I called printf. Like, what the? Yeah. So we added a feature that was from the cough linker for cough. Who uses cough? PE cough is Windows, I think. PE is a cough. I don't remember who uses cough. I think it's PE. Anyway, yeah, we added a feature from that called ylive. Or ylive. There was an argument in the code review for this on whether it was ylive or ylive or yalive, or naming things is bad. Anyway, you can say ylive printf, and it will basically trace the path that is keeping this alive from the point of view of the garbage collector. Oh, it's alive because main calls printf, and start, the entry point of your program, calls main. And it'll give you one of these paths for any symbol that you care to ask about. And this is incredibly useful for debugging these kinds of things. It's also useful, in the LLVM-MOS context, because the same thing happens. You call something, and you don't know why you brought some random function in from the SDK, and you can find the exact place in your program that calls it, even indirectly. Another big thing that I'm working on actively upstream right now is modular printf. And this is something I'm very proud of. It's not originally my idea. This was from an ARM toolchain and linker, but we're trying to make it a general feature that will exist in Clang going forward. So if you don't know, printf is huge because it's got to do a lot of stuff. But most programs only do some of the stuff. You might just do %d 42, print a number. And to me, this should compile down to a little loop that prints 4 and then 2. And it can't, because all of the printf nonsense has to come with it. And the compiler doesn't have a prayer of seeing through the stuff that parses %d and redirects that information down to the thing that actually does the %d logic. So what we're working on is a compiler transform that whenever it can tell, oh, this call uses %d, it would redirect that to a modular printf function and a token that says this is using %d. The link would then be able to collect and sum together all of the tokens from all of the program to see what parts of printf are used and what parts are not. And then modular printf would be designed in such a way that the linker only brings in aspects of the implementation that you actually end up using. So this would get us a lot closer to being able to have a printf, 42 hello world kind of thing, or I like hello %d 6502. That's my go-to demo. I'd like that to be like 100 bytes, and I think one day we'll be able to actually get there. It's been very slow to get through code review because nobody's sure who wants this or why, and I have to tell them that embedded developers exist and kilobytes still matter. But yeah, we're working on that. And here's where I talk about all the stuff that I want to do in LLVM-MOS but haven't had the time. We need a new register allocator. LLVM's register allocator was not designed to 6502. It just does not, it's not aware of any of the constraints that drive us. So really, from instruction selection afterwards, we should be doing things ourselves. Like that section of the pipeline is just not very well suited for our purposes. Everything before is fine. Even its instruction selector, I've had no trouble with. But that little middle section is just brutally broken, and I need to rewrite it. But this is rewriting a major section of a major compiler framework from scratch to get it to work good on the 6502. And it's doable. It's what all of the other guys that are writing 6502 compilers have done. They've done great jobs of it. It's just a lot of work, and I have increasingly little time as time goes on. So I have been ostensibly working on this for more than a year. I will do it someday. Fingers crossed. As I mentioned, the other big thing that I wanted to work on was automatic banking. To access code and data, you need the state of the system to be correct to access that code and data. So we wanted the compiler to be automatically able to emit switches to, get that state right. And this is the thing that would allow us to use the section class nomenclature feature of the linker to automatically place things and then have the compiler automatically switch to the right bank. And then you'd be able to make very big NES games completely automatically without having to lay out anything at all yourself. Oh, and John Bird is working on a debugger. LLDV, you might be able to hook it up to an emulator and get source level debugging where you can printf individual variables and do breakpoints and stuff. He had a demo of this, which is very cool. But the main issue there is that we have not made any effort to keep our dwarf coming out of the compiler working. So that's also a big ball of work. Also, all of you that are here for this talk, and I'm a little late, please write an Apple II target. For some reason, we don't have an Apple II target. No one's written one. I don't know anything about the Apple II. I don't think it's that hard to add one, but there's like a million of them. I don't know what ProDOS is. So please help. Please write an Apple II target if you're interested. Otherwise, that's it. Thank you very much for coming. Thanks for listening. Okay, we have about 5 minutes for questions. Please come up to the mic. Should be on.
Hello. First of all, thank you for making MMC1 easy to use. I've dealt with that myself. It's, not fun. But my real question is, so of all the complications that make the 6502 a difficult target for C, the one I think about the most is that C kind of expects array of struct layout, and 6502 programmers, at least in assembly, the instruction set tends to work better with arrays of individual bytes of the structure splayed out like that. Do you do anything in the compiler to account for that? Or
we don't. I thought about adding it as a compiler feature, and admittedly, there is upstream work, believe it or not, to create a SOA optimization. But it drew some ire for the compiler community. What we did instead, there is in our SDK, I think I wrote it. Yeah, there's an SOA library in C++, and you can wrap any array that you like, and it will turn that array of structs into instructive arrays. Yeah. So this has actually been used in a couple games. You also can have pointers into the structive array, which are actually indexes into the array of structs. And it gives you more or less native access as if it were in the layout that you'd expect in C++, but internally it compiles down through horrible C++ template nonsense to structs of arrays. And it worked well enough that I didn't really go looking for a compiler solution. It's not great to tell people you have to use C++, but you can also just kind of retrofit a little bit of C++ onto a C project, and it'll work mostly fine. So I think I'm happy with that. I've used it in my projects. Hopefully that answers the concern.
That's really cool. Thank you.
Yeah.
Hello. You mentioned you'd like one day for the, you said printf hello %d 6502 or something, whatever your example was. You said eventually you'd like it to be down to like 100 bytes. How many bytes is it nowadays?
I think CC65s, which is written in hand assembly, is 2K. Ours is around 4K, but it's in pure C. So it's not even that big, but it's just way bigger than it should be. And that's bad.
Was there a particular platform that motivated you to start this project? Or do you have a preferred target that you like to work with?
To me, I started it because I'm a compiler guy. I was interested in this rhetoric that people had that you can't compile good code for the 6502. And incidentally, like I didn't actually write the linker or assembler parts. Those were written by John Bird, and we actually ended up merging my compiler backend with his linker and assembler support. And people have been interested in an LLVM thing for this, but for me, mostly the SDK was to make sure that this thing got used, that what we made we thought was good, and it was important to allow people to use it to do cool stuff. So I've mostly, honestly, been interested in the compiler stuff, and I got most interested in the NES just because of how hard it was, again, from the compiler and linker point of view. Now, I did end up making a bunch of weird NES hacks afterwards, so I'd have to say the NES, I guess, just because, yeah.
Thanks.
So you would mention that the debugger was not current. So 2 questions. 1, you would mention that the debugger was not currently working. What all would need to be done to get that up and running?
Okay, so I think John has already done the preliminary work for that. It is that first you need to teach the debugger about the system, like where pointers are, what the stack pointer is, like stuff like that. And I think half of that works, the other half doesn't. There are cases where it'll just get confused and say, I don't know anything about anything. Since it's a debugger, like it's pretty flexible that way. Really, most of the work is that it'll say, I just don't know where this variable is. And it'll say, I don't know where this variable is because the passes that we wrote in LLVM-MOS just drop information about where variables are. Like you have to add a lot of code to these compiler pipelines to, as you massage things, massage the debug information along with it in exactly the same way so that it stays current. And we just didn't do it. And LLVM is very conservative. It's like, oh, I don't know what this debug information is, so this variable, question mark? And now that's actually a problem in upstream compilers too. Like LLVM notably does not produce as good of debug information as GCC does. And it's kind of a sore spot that there's just stuff that it will forget about where variables got put. And that actually affects people upstream too. So I think that's most of the work, honestly.
Okay. And then my next question, it's still on topic, but if anybody knows of any good debuggers, live debuggers for coding in 6502, please let me know because I'm looking for one.
Mezen probably is the best that I know of.
Mezen? Okay.
For the NES, but that's just for the NES, unfortunately.
Okay. I will talk to you after the talk then.
Okay.
Thank you for a very interesting talk. Question about 65.8.16 support. There's been a little discussion of this in the issues on GitHub, and I'm wondering where that stands. It's complicated, I know.
I know. I didn't expect anyone to ask this, so thank you. Like, you've been keeping track of it. Okay, so the 65, here's my stance on this. I know it's something that people really, really want. 2 things. 1, it was only used in 2 commercial systems of any major import, which makes it rough. Like, they're 2 beloved systems, though. They're the SNES, what's the SNES, and the Apple IIgs. People love the 2GS. But it's just those 2 systems, and it's a whole new chip. Like the difference between it and this, like in terms of a compiler and the 6502, it's comparable to the like 8-bit 8080 or Z80 and the x86. Mm-hmm. Like it's basically a segmented processor. Like it requires a completely different compilation approach to the point where I am doubtful that it would actually end up sharing much code with the backend that we wrote, other than just naming and boilerplate. So like to me, supporting the 65.8.16 in a way beyond what we've done, where you can just compile 6502 code for it, is a commensurate amount of effort to all of the stuff that we've put into the compiler so far. So I'd welcome people that are interested in doing that. I don't have the energy to, honestly.
Great. Thank you.
Mm-hmm. Okay, I think that's it. So I'll pass off to the next person. Thank you very much.